So we are going to go with the topic of bearings with probability of survival higher than 90%. Up till now, we were doing that. We were finding the rating life means when 90% of bearings were working and before the first sign of failure was shown, how many of number of revolutions or hours were completed by this 90% of bearings. That life we used to find out, which was L10. But what if the probability is other than 90%, higher than 90%, say 95%, 96%, 98%, 99%, then what would be the life at that reliability, higher reliability that we want to find out. But before that, how is reliability defined? It is the ratio of number of bearings which successfully completed L million revolutions divided by total number of bearings under test. And if I want to show this to you mathematically, then it is shown by this way. Number of bearings which successfully completed L million revolutions divided by total number of bearings under test, right? So if I increase the reliability, then with increase in reliability, the life of the bearings predicted will be reduced as the larger number of bearings is to reach that life, right? So if a better is, I should find out a relationship between reliability and life of the bearings. And how is that done? It is predicted by Weibull distribution, right? And what does Weibull distribution state? It states that, and it is shown by this graph, where on x-axis there is L upon L10, and on y-axis there is percentage of bearings in operation. So how is this Weibull? What does this Weibull distribution state? It states the relationship between reliability and life. R stands for reliability and L stands for corresponding life. A and B are constants. So what does this Weibull distribution say? It says that reliability is exponential e raised to minus L upon a raised to b, or it is the exponential of minus L upon a raised to b, where a and b are constants, L is the life, corresponding life, and R is the reliability in fraction. Now let me find out this L by L10, right? I want to find out this L by L10 ratio. So I'll simplify this equation, right? How will I do that? If I want to remove this minus sign, this side it will become 1 upon R, right? So let's do it. You can see here, right? This minus sign is removed from here. 1 upon R is e raised to L upon a raised to b. If I still want to remove this e or exponential, then this side it will become natural log of 1 upon R is equal to L upon a raised to b, right? What if I want to express L10 life at 90% reliability, right? Then it will be log e of 1 upon, see, 90% reliability means 0.9. So I'm writing down here 0.9. Log of 1 upon 0.9 is equal to L10 upon a raised to b. So this equation 1 was for other than 90% reliability, and this equation is at 90% reliability. So when I divide equation 1 by equation 2, right? When I divide equation 1 by equation 2, I am going to get the final relationship between life and reliability of rolling contact bearings, which is L upon L10 because AA will get cancelled from here, right? So L upon L10 is ln of 1 upon R divided by ln of 1 by R90. And what is R90? R90 is 0.9. So guys, this is our final relationship, this one, between life and reliability of rolling contact bearings. I'll again pronounce it. L upon L10 is natural log of 1 upon R divided by natural log of 1 upon R90 raised to 1 upon B. We are going to do numericals on this other than 90% reliability now, right? So guys, in this equation which we derived, right? In that equation which we derived, R90 is 0.9 here, right? A is 0.64, though A has got cancelled here since we divided equation 1 by equation 2, A got cancelled, and the value of B is 1.17, right? So since it is 1 upon B, so it is 1 upon 1.17. So when I put this value of log E, natural log of 1 upon 0.9, I'm going to get as 9.491 natural log of 1 upon R raised to 1 upon 1.17. So you can either use that formula which we derived, or you can simplify and use this formula. It's one and the same, right? So if I want to find out median life, see, if I want to find out life at 50% reliability, then I don't need to use this equation because L50 is nothing but 5 times the rating life, which is L10, right? But other than 90% reliability, right? Suppose the reliability is 99%, right? Reliability is 99%. Then how much life will be at 99%? Or say if life at 99% reliability is this, then find out the rated life. That would be the thing which we are going to do in our numericals. So let's proceed. How this has come, I already told you, right? I just have to put here 0.9. I have to do 1 divided by 0.9. I have to take natural log of it, right? Then I'm going to get 9.491 log, natural log of 1 upon R raised to 1 upon 1.7. So there shouldn't be any confusion. You can either use this one or this one. It's one and the same thing. Above equation is used for selecting bearing when reliability is other than 99%. So if reliability is, other than 90%. So if reliability is 98%, 99%, 95%, then you should use the above equation which we have derived, right? Now, what if in numerical it is asked that find out the reliability of a complete bearing system? Complete bearing system is that in a machine, right, which is assembled, other than just one bearing, there would be 4 bearings, there would be 5 bearings, there would be 6 bearings. Then you would be told to find out the reliability of this complete system, which consists of 4, 5, or 6 bearings. Then in that case, suppose the bearings, the number of bearings in this system are 4. Then you will find out reliability of 4 bearings. If there are 5 number of bearings, then you are going to find out the reliability of complete system as R raised to 5. So Rn is equal to R raised to n. This is the reliability of the complete bearing system. We are going to do numericals on this. So further, when we'll do the numericals, we'll come to, right, where Rn is the probability of 1 out of n number of bearings failing during its lifetime. Now, guys, what if adjusted life bearing? Such sort of numericals are asked. Now, what is this? Many a times the actual life of bearing is less than the rating life, right? Actual life is less than the rating life, L10. Why? Because the required reliability is higher than 90%. severe operating conditions like temperature, humidity, requirement of different bearing materials in specific applications. So if this happens that actual life is less than the rating life, then you have to do what? You have to calculate the adjusted life of the bearings, which is LE in million revolutions, right? So A1, A2, A3 are life adjustment factors, which you have to multiply it by with that rating life, right? A1 is life adjustment factor for reliability, which is taken as 4.48 log E 1 upon R raised to 1 divided by 1.5. A2 is life adjustment factor for operating conditions. A3 is life adjustment factor for bearing materials. Don't worry, you would not be asked to do this, right? Life adjustment factors, A1 is given here. So you don't have to use this equation. A1 you can find out from here, right? So life adjustment factor A1 at 90% reliability is 1. A1 at 91% reliability is 0.928. 92% reliability is 0.855. So A1, A2, A3 are life adjustment factors for different conditions, like what if for reliability, for operating conditions like temperature, humidity, for different bearing materials for different operations. This A1, A2, A3 factors are there, right? Then how would you find out the actual life, right? You are going to multiply those factors. That is what you are going to do. So such numericals are also going to come at that time, we will see. Now, if numericals on life of bearing other than 90% are going to come in exam, then what formulas you should use, right? A common formula of rating life conversion from hours to million revolutions. You already know this is life in million revolutions. This is life in hours. So L10 is life in hours into 60 into revolutions per minute of the shaft N divided by 10 raised to 6. Same is going to work for L99 million revolutions. Then it will be L99H into 60 into N divided by 10 raised to 6. Same way, L95 will be L95H into 60 into N divided by 10 raised to 6. So what I'm trying to say is that the conversion of million revolutions to hours, whichever reliability it is, 90, 95, 99, the formula is still going to remain same, right? But if life other than 90% has to be found out, then we are going to use this formula, which we did the derivation right now. Life reliability derivation, L upon L10 is log E 1 upon R divided by log E. Log E is actually natural log, right? Natural log of 1 upon R90 raised to 1 upon B. So these two formulas we have to remember. So if 99% reliability is there, right, then L99, or you can write down L01H is equal to log E of 1 upon R99 divided by log E of 1 upon R90 raised to 1 upon 1.7. 99% reliability, 99%. So 99 divided by 100, that will become 0.9. Same way 0.90, right, divided by 1.17. Then you will get L99 divided by L10, right? So I showed you for 99% reliability. What about if it is 95% reliability? Then obviously here it will be 95% reliability, right? So you'll put the value of 95% reliability, right? And you will get the value. Now see, here I have done what? I have taken one example. What you are going to do in your numericals, which are asked. In numericals, they'll tell you that find out the rating life if the life at 95% reliability was 10,000 million revolutions. I'm just taken one random value. If in numerical is asked that life at 95% reliability was 10,000 million revolutions, then find out the life at 90% reliability. I'm again repeating. life for 95% reliability is this much, then find out the life for 90% reliability. Then in that case, what you'll do, you will put the value of life at 95% reliability, which is given 10,000. You will put here 95, right? 0.95. You'll put here 0.90. You'll do this whole simplification. L10 will go here in the numerator. This whole will come divided by, right, 10,000 divided by something. And then you will find out life at L10. Such numericals are asked in exams. Without wasting time, again in that equation, if most of you did not understand which equation I'm talking about this equation. If you want to already simplify this, then put here 0.90, right? Find out the natural log and simplify this equation. How to simplify it? We'll do it here for you so that will become easy, right? What is in denominator natural log of 1 upon 0.90? First in your calculator, do natural log of 1 upon 0.90. It will come 0.105. Then divide this 1 divided by 0.105. You will get 9.491, right? And that's why that formula is coming L upon L10, 9.491 natural log of 1 upon R raised to 1 divided by 1.17, right? So either use any of the formulas, your answer will come. Now let us proceed with the numericals which are asked in our exam. 14th numerical, right? 1 to 13 I've already solved before. You can see my previous videos, which I'll also put down in the description box. You can easily find out. Deep groove ball bearing. Whenever the ball bearing is there, remember our A or P is 3. What is A or P? In our load life relationship, right? What is our load life relationship? L10 is C upon PE raised to A or P. This A or P is 3 when it is a ball bearing. So A is 3, that is what is given to you. A deep groove ball bearing for shaft diameter of 50 mm. Sorry, 60 mm. Shaft diameter is given. And see, they have told us to find out suitable bearing from manufacturer's catalog. So if you have to select a bearing, you will require shaft diameter. See, guys, how this numerical is other than 90%. See, they have this time given reliability at 90%, right? So this is the numerical of other than 90% reliability. So 98% rotates at 1440 RPM. Shaft RPM N is given. Small n is given 1440 RPM or capital N in some ways. Radial load FR. Thrust load FA. Expected life of bearing at this 98% reliability is 25,000 hours. Service factor KA or S. This time they have given 1.2 and they are telling us to find out suitable bearing from manufacturer's catalog. So let us quickly write down the given data. First, they have given us the diameter. They have told us at reliability 98%, the shaft is rotating at this much RPM, N RPM. Radial load is given, axial load is given, thrust load is given, and at L98 hours, reliability 98, the life L98 in hours is 2500 hours. Remember, we have to always convert hours in million revolutions. So we'll use a suitable formula. And load factor S or KA, right? Shock load factor or load factor or load application factor is 1.2, right? So let's start, guys. This time, first, when you see here, notice the numerical X and Y values are not given. So guys, actually, the numerical is this, right? This table is not given. This table is there in Bhandari Design Data Book, right? So that table you have to use the table for X and Y factors for deep groove ball bearing. That table in the design data book you have to use. And for that, first we will require what? We will require FA upon FR, and we will require FA upon CO. These two factors we will have to first calculate, and from that we will find out X and Y factors. So let's start. Let us first find out FA upon FR. So FA is given in numerical 1200. FR is also given data. So that becomes 0.48. And you can see this E value is 0.44. So our FA upon FR, which turned out to be 0.48, is greater than this E value, which is 0.44. Hence, we are going to take this FA upon FR is greater than E. Right? Because you can see 0.44 is less, 0.48 is more, it is greater than E. 0.48 is more than 0.44. That's why we are using this table now. Now, when you notice this table, first thing which you definitely understood is that X value is common everywhere, which is 0.56. But what about Y value? For that, you have to see FA upon CO. But CO is not given, right? So if CO is not given, you can find out from bearing number from design data book. But here bearing number is also not given. Then you will take this last line, which is X is 0.56 and Y is 1. So we will take Y as 1. So we found out our X and Y values. Now we will use our equivalent load equation. What is our equivalent load PEQ or PE? It is XVFR plus YFA into S. V is our race rotation factor. We assume V as 1 when inner race rotates, and we assume V as 1.2 when outer race rotates, but here nothing is given. So we will assume 1, we will assume inner race rotates, and we will assume V as 1. That's why I'm not written here, right? So V is 1, right? So X, we right now found out from the table. What did we find out? We found out X as 0.56. FR is given in the numerical 2500. Y we found out from the table, which is 1. FA is 1200 and S is given in the numerical, which is 1.2. So our equivalent load PEQ or PE, in some books it is denoted by PEQ, in some books it is denoted by PE. We found out equivalent dynamic load PE as 3120 Newton. Now, finding life of bearing at 98% reliability. See, this equation is given in the Bhandari design data book, 60 NLH divided by 10 raised to 6, right? So 60 into 1440 given in the numerical divided by life at 98% reliability is also given 25000, right? So L98 is 2.16 into 10 raised to 9 revolutions, and if I divide it by 10 raised to 6, it will become 2.16 into 10 raised to 3 million revolutions. This is our answer. We found out L98, right? Now, once you find out L98, we have to find out L10. So we will use our formula of L upon L10 is 9.491 log E, natural log of 1 upon R raised to 1 upon 1.17. So we will put this value. We found out life at 98% reliability in million revolutions. Right now only found out, right? So if we put this in million revolutions, I'll get the answer in million revolutions. But if I'm putting here the life in revolutions, I'll get the answer in revolutions. Better we stick to our, you put down the answer in million revolutions, right? So 2.16 into 10 raised to 3 divided by L10 is 9.491 natural log of 98% reliability is there. So 0.98 raised to 1 upon B, that is 1 upon 1.17. You will get the answer as 8.862 into 10 raised to 3 million revolutions. This was our answer, right? Now we want to find out the dynamic load. How? With our load life relationship. What is our load life relationship? L10 is C upon PE raised to A. We found out L10 as 8.862 into 10 raised to 3 million revolutions. We have already found out equivalent load previously. So our unknown is C. Let us find out, right? So I'm going to use this equation now. So L10 upon C, L10 is equal to C upon P raised to 3. 3 because it is a numerical of deep groove ball bearing. If it was a numerical of roller bearing, I would have written 10 by 3. But it is a ball bearing, that's why I'm writing 3. So if I'll put here million revolutions, that would be the correct answer. So I should put here million revolutions, sorry, it's 3, not this. So I'll put here 3, then I don't need to multiply it by 10 raised to 6. But if you put in revolutions, you have to multiply it by 10 raised to 6. So let's keep in million revolutions. L10 is C upon PE raised to A. So 8.862 into 10 raised to 3 is equal to C upon P is 3120 Newton raised to 3, which is our A, right? When 3 will go this side, this whole thing will become 1 by 3 and this will be multiplied by 3120. You will get the answer as C, and your answer for C is 64.56 into 10 raised to 3. It's not over. You have to go to Bhandari design data book, and in deep groove ball bearing, in front of 60 mm diameter, for dynamic load of this much 64560 or greater than that, you will see this line of 6312, and then you will find out that this bearing is suitable bearing which can take the load or dynamic load carrying capacity of 64560. That's why we will choose SKF 6312. How is that done? That also we have done for you here. We will go for the table in Bhandari design data book of deep groove ball bearing. The tables looks like this. We will go for 60 mm shaft because that's what is given in our numerical. We found out C as 64560. So in 60 mm, there is nothing like 64560 Newton, right? But the higher value than that is 81900. Value higher than 64560 is 81900. You have to see the C value. You don't have to see the CO value. We are finding bearing on the basis of C. So 81900 is bigger than 64560. That's why we are choosing this bearing 6312. This is the end of the numerical. Very quickly, let us go to next numerical, number 15. Ball bearing is subjected. Ball bearing, again, A is 3. If it was roller bearing, we would have taken A as 10 by 3. But this is a ball bearing, so we will take A as 3. Subjected to radial load 4000 Newton. Now, why I have done equivalent load is equal to radial load? See, guys, they have not mentioned axial load at all. So if axial load is not given, axial load factor will become 0, right? And if it is a purely radial load, then I'll show you here P is X VFR plus YFA. This is our equation. If radial load is not given, this whole thing will become 0. Purely radial load, so this will become 1. Nothing is mentioned regarding V, whether it is in this whole numerical, nothing is mentioned whether Outer race rotates, inner race rotates. We will assume inner race rotates. We will assume V is equal to 1. So 1 into 4,000 will become radial load is equal to equivalent dynamic load. That's why I've written PE is equal to FR is equal to 4,000 Newton. Expected to satisfactory life of 1,000 hours at 95% reliability, right? What is L95 or L05H? It is 12,000 hours. N RPM is given 720. You have to calculate dynamic load carrying capacity, which is C, right? And you have to see that it is selected from a manufacturer's catalog, but we won't be able to find out the actual bearing because neither shaft diameter is given nor the bearing table number is given, right? So we will just find out C. Not just that, they have told that if there are 4 such bearings, each with the reliability of 95%, then you have to find out the system reliability. That is the reliability of a complete system, right? So let's start. First, let's find out L10. Why? Life at 95% reliability is given. Then let's find out life at 95% reliability in million revolutions. So that is denoted by L05. So L05H is 60 into N divided by. Now the question in your mind will be, why are we writing down this L05? See, at 95%, if we are writing L10, then at 90% reliability, if we are writing L10, then obviously at 95% reliability, we are going to write down L05 because 90 plus 10 is 100. Then 95 plus 05 will be 100, right? So L05 into 60 into N divided by 10 raised to 6. L05 is given in your numerical 12,000. RPM, shaft RPM is given 720 divided by 10 raised to 6. If you won't get the life in million revolutions. We will get the life in revolutions. So that's why to get the life in million revolutions, we have divided by 10 raised to 6. So we came out to be 518.4 million revolutions. So guys, in this formula given below, we found out this life at 95% reliability, which is 518.4. So from that we can find out L10 rated life. So let's do it, right? So let's go ahead. I have this life right now. I found out, which is 518.4. Reliability is given 95%. So I'm going to put here 0.95. Right? So once you simplify this way, step by step, like I have done, and you put down the values in your calculator, you will get L10 as 959.10 million revolutions. Step by step simplification, simple maths you have to do. That's it. Now, if I found out L10, if I have PE, next I have to do is that I have to find out dynamic load carrying capacities. L10, right now I found out, which was 9.1 million revolutions. PE, which is equal to FR in this numerical, which is 4,000. It's given in the numerical, right? When 3 will go this side, it will become 959.1 raised to 1 by 3. 4,000 will go here and get multiplied this way. You will get C. So do this in your calculator. You should be getting the answer as C is 39447.10. Also, 4 bearings are there. So you have to find out system reliability. So R raised to N. There are 4 bearings. So 0.95, 95% reliability, they have already told you. So 0.95 raised to 4 will become 0.8145. So the reliability of the complete system, which consists of 4 bearings, that is 81.45%. This is your system reliability. Let's very quickly go to numerical 16. Right? We have done numerical 14. We have done numerical 15. Let us go to numerical 16. Deep groove ball bearing. Again, ball bearing is equal to 3. Number is already given 64808. Right? Selected for a shaft 40 mm diameter. Shaft diameter this time they have given. Running at 1000 RPM. Required bearing life is 5000 hours. So this reliability is at 99%. So L01 is 99%, life at 99%, and it's in hours. That's why I'm going to write down H. Right? Next, radial load is given, axial load is given, it's given in kilonewton. You should be converting it into Newton like I have done. Check, is bearing suitable for this application? Is this bearing which is given that is suitable for operation? Or you should select other bearing. That's what they have told us to do in this numerical. Let's do it. First thing is that, guys, in front of deep groove ball bearing table in your Bhandari design data book, in front of this 6408, you should find out C. You should find out CO values. C is 63700 and 36500. Remember, 40 mm is the shaft diameter. That's why in front of 40 mm and 6408 bearing number, which both are given in the numerical, in front of them, I'm noting down the value of C and CO. Now, what did I find out? That for this bearing, CO 6408, CO is 36500 and C is 63700. X and Y are not given. So I have to find out from this table 15.9 in the Bhandari design data book. FA upon CO. CO, where did I find out? From the table previously, in front of 40 mm diameter and bearing number 6408. Remember, CO value was there at the top. C value was there at the top. CO, we had noted down this. So we are putting here. FA is already given in the numerical. So this becomes 0.03287. And FA upon FR, V is always 1 whenever it's not given. Right? Its inner race rotates, we will assume, since nothing is given. So we will assume V as 1. So this ratio comes out to be 0.48. FA is also given, FR is also given. So that ratio came out to be 0.48. Now, first, what you should do, you should first see whether FA upon FR is greater than E or FA upon FR is less than E. If you see FA upon FR is 0.40, is 0.48, and it is greater than this E value, which is 0.44. So we are going to take this. I've written here. It's greater than 0.44. So we are going to choose this table. Everywhere X is 0.56. So it's clear. X is 0.56, right? What about Y? Y we can find out from FA upon CO, right? Now it is 0.32, sorry, 0.03287. Now see 0.03 will lie between here somewhere, 0.032. So we will have to do interpolation and we have to find out our Y value. So let's do it, right? Like I said, you have to find this 0.3287, which lies between these two values, right? So we have to do our interpolation. Let's start, right? Now, if I take this value as x1, right, 0.025, then in front of that, y is 2. If I take this value as x2, which is 0.04, then in front of that, this y value is 1.8. And what is the value for which I want to find out? 0.03287, which is in between these two values. So I'll write down in between. And for that, I need to find out y. Now, very quickly, what you have to do, you just have to call this as x1, then this will become y1. This is xr, then you have to find out yr. This is x2, then this is y2. Put down all these values in this. Y1 minus Y2 upon X1 minus X2 is Y1 minus YR upon X1 minus XR. This is our interpolation formula. Once you put down the values properly, like I have done, you will get the value of YR or Y in front of 0.328, 0.03287, which is 1.895. So guys, we have calculated X value also. We have calculated Y value also. X value turned out to be 0.56. Y value turned out to be 1.895. Now, what are we going to do? We are going to use our equivalent dynamic load equation, PE, which is there in Bhandari design data book. X, right now we found out 0.56. V is 1. Nothing is written whether inner race rotates, outer race rotates. So I will assume inner race rotates. I'll assume V is equal to 1. FR is given in the numerical. Y we right now found out from the table. FA is given in the numerical. So once you simplify it properly, put the brackets. Otherwise, you will get wrong answer. This is how you should put the bracket. First multiply 0.56 into 1 into 2.5 to 10 raised to 3. Then add it with bracket of 1.895 into 1.2 into 10 raised to 3. You should be getting the answer 3674 Newton. Now, the problem is we don't have L10. We have life at 99% reliability, but we do not have life at the 90% reliability. Then what you should do? First, you should find out what? You should find out life in million revolutions. Right? Now, if I put down hours over here, here also it will become hours in denominator. So 5,000 hours is the life at 99% reliability. Here I'm going to put 0.99 because it is reliability 99%. Here I'm going to put 0.90 because the life is at reliability is 0.90. Once I simplify this, what will I do? I'll put down L10H will go over here. And this whole thing will go down in the denominator of 5,000. Then I'll get the life in hours, L10H as this. But I want life in million revolutions. Then I'm going to use this formula, L10H into 60 into N divided by 10 raised to 6. This value I'll put down over here. N is given in the numerical, which is 1000 RPM. Then I'm going to get L10 as 2235.3275 million revolutions, which I'm going to put down here in the load life relationship, right? So if L10 is CR upon P, CR because I'm going to already from bearing table, I found out C as this much. Then what is CR, right? That I should find out. So CR I found out as 48038 point. Required dynamic capacity is 4803 and basic is 63. Now basic should be higher than required. Then your bearing is suitable. So it is like that only. Your basic is 63700 and it is greater than what we calculated, which is 48038.14. Hence, this bearing which is given 6408, that is suitable for your application. Very, very easy numerical. Let's proceed to the next numerical, right? The next numerical is numerical which was asked recently in summer 2022. Recently asked numerical, right? And very important because it has adjustment factors, right? A1, A2, A3. So let's start. Rolling contact ball bearing. Again, ball bearing. So A is going to be 3. P is going to be 3. A, B, K, whatever you write down, right? Overhung shaft, the shaft speed, N RPM is 720. 99% reliability, the life is 2400. So L01H is 24000 hours. From this, we can find out L10. This time they have told that equivalent radial load is 1 kilonewton. Now that thing is mentioned about axial load. So in this equation, P is equal to XVFR plus YFA. Axial load is not given, so it is 0. FR is given, right? Which is 1 kilonewton, so 1000 Newton, purely radial load. So X will become 1. And your V, race rotation factor, nothing is mentioned. So we will assume inner race rotates, we will assume V as 1. So our equivalent load will be equal to radial load, which is 1000 Newton. Adjustment factors are given this time. What you should do for the life adjustment factors for operating condition, temperature condition, and materials, different bearing materials for different particular applications, that factors are given, right? They are telling us to find out C, basic dynamic load rating at 90% reliability, right? Let us start. What should we do first? We are going to find out the life in million revolutions. It is given in hours at 99% reliability. Let us find out in million revolutions. So it's given in hours. When you use this equation, which is there on Bhandari Design Data Book page, right? 60 into N into LH divided by 10 raised to 6. You have to do this 10 raised to 6. Then you will get the life in million revolutions. So you find out as 1036.8 million revolutions. Now, what are we going to do? We are going to find out this L90, because this we found out in million revolutions, right? But we have not found out L90. But when you use this, you have to multiply these two adjustment factors with your common formula, right? So I'm going to multiply this over here, right? So 99% reliability, it is 0.99. 90% reliability is 0.9. Natural log of 1 upon 0.99 is this much. Natural log of 1 upon 0.9 is this much, divided by, raised to, when you'll do this, it will come 0.8547. So L99 upon L90 came out to be this much when you have multiplied with adjustment factors. So L90, if I want, then L90 will come here and this will go in denominator like this. And you know, L99, we already found out in the previous step, which was 1036.8 million revolutions. So you found out L90 as 10105 million revolutions. Now we have to find out C. So we'll use the simple load life relationship. This we right now found out, million revolutions. Since it is a ball bearing, this is going to be 3. 3 when it goes this side, it will become 1 by 3. T is 1000, so it will get multiplied over here. So you get the answer as 21619.5 Newton. Basic dynamic load carrying capacity or basic dynamic load rating. That is our C. Let's go to the 18th numerical, right? Which is single row deep groove ball bearing. Again, is 3. Subjected to radial load FR, thrust load FA. X and Y factors are already given. Shaft speed N is given. Diameter of shaft is given. The bearing number is given, and in front of that bearing number C is also given. You have to find out the life of bearing with 90% reliability. Estimate the reliability of 20,000 hours of life. Let's start, right? How should we proceed? We have to first find out PE. Why? FR is given, FA is given, X is given, Y is given. So obviously that is a hint. You should find out equivalent dynamic load first. So let us do it. X VFR plus Y FA into S or K. S or K, nothing is mentioned. So we will assume 1. V, nothing is mentioned. Inner race rotates, outer race rotates. Then we will assume this V as 1. Inner race rotates, right? So X is given in the numerical 0.56. Your radial load is 8,000. Y is given. FA is given. Simplify, you will get the answer as 8980. In load life relationship, we will find out C. We have already there in the numerical. P we right now found out raised to 3. That will become 1940.10 million revolutions. Life in million revolutions is there, but I want life in hours. So what is my formula? L10 is L10H into 60 into N divided by 10 raised to 6. Right? So if I want L10H, this will go and multiply here, L10 into 10 raised to 6, and this 60 by 9 will go down in the denominator like this. Right? So I will get the life as 26945.83 hours. I wanted the life in hours. Right? Now, why I want the life in hours? Because the other life is also in hours. That's why I have done this conversion into hours. Right? So L is given. L10 we found out. Right? R is what we need. R90 will become 0.90. So substitute all these values and you will get the reliability as 92.83% for 20,000 hours of life. Let's go with another numerical. 19th numerical. Ball bearing, again 3. Radial load of 5 kilonewton. Axial load is not given. X not given. Y not given. Then we will cover this as P is 5. See guys, this is almost similar to the numerical which I have solved 5th numerical before. Same data was there, but instead of here 99, that we had solved for 90% reliability. Same data, right? But here it is 99%, right? So this 8,000 will be for 99% reliability, 8,000 hours. Life will be for 99% reliability. So now one step has increased as compared to numerical 5, right? What we are going to do? Life at 99% reliability in hours is 8,000 into 60 into N is given in the numerical. 1450 divided by 10 raised to 6. So L95 is 696. Sorry, L99. It's a typo error. L99 is 696 million revolutions. So 696, R99 is going to be 0.99. R90 is going to be 0.9 and B value is 1.17. Put down this natural log of 1 upon 0.99, you will get this answer. Put down natural log of 1 divided by 0.9, you will get this answer. Do 1 divided by 1.17, you will get this answer. L10 will go here and this whole thing will go 699 divided by this much. You will get the answer as 5186 million revolutions. L10 we found out. Now at this L10, I want to find out dynamic load carrying capacity. So we will use load life relationship formula. L is C upon P. L we right now found out. P is our purely radial load, which is 5,000. 3 when it goes here, it will become 1.3 and this 5,000 will multiply here. So you will get C as 86546 Newton. Dynamic load carrying capacity, dynamic load rating, that is C. Very quickly, last numerical, very quickly. Again, deep groove ball bearing is 3. Subjected to radial force, FR is given. Axial load, FA is given, X and Y factors are given, N is 12,000, bearing number is given, and in front of that bearing number C is already given. Diameter is 75 mm, right? We have to do what? We have to calculate two things. Life of bearing with 90% reliability, that is rated life L10, and estimate the reliability if the life is 20,000 hours. So we have to calculate R. Let's do it very quickly. It's very easy numerical, just like previous numericals. Combo of previous numericals is this numericals. Whenever X is given, Y is given, FA is given, FR is given, your first thing is you have to find out equivalent load. What is our formula? XVFR, YFA into S. S or KA, our load application factor, load factor, nothing is given, we will assume 1. Race rotation factor, nothing is given, we will assume inner race rotates, V is 1. So you will get this as 8980 Newton. Next, L10, right? Since in our numerical C is also given, P we found out. So L10 in million revolutions is 1940.10 million revolutions, right? This was our first step. This was the first answer that they were expecting from us, right? Now, L10H I want, because reliability for 20,000 hours they want. So I have to convert this million revolutions also in hours. So L10 into 10 raised to 6. How? We have a simple formula. L10 is L10H into 60 into N divided by 10 raised to 6. So if I want this, then it will be L10. This will go here into 10 raised to 6 is equal to L10H. And this whole will go down. So this will be 60 into N. This way. You will get 45.83 hours. Now, at 20,000 hours, what is the reliability that we want to find out? So, we will use this formula. We have life 20,000 hours. We have found out L10 in hours right now, 626,945.83. We want to find out this when this is 0.90. Put down all these values. This 1 upon 1.17 will, it goes this side, will just become 1.17, right? Simplify this step by step properly, and you will get the answer as 0.92. That is 92.83%. These are the end of the numericals of probability other than 90%. Thank you.